Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project, which is part of the IDEAS-ECP computing project of the United States U.S. Department of Energy. This series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Lab. I'm Osni Marcus from Lawrence Berkeley Lab, and I'll be the host for today's webinar, Software Design for Longevity with Performance Portability. This is the 40th webinar in this series. The webinar today will be presented by Anshu Dubey. Anshu is a computer scientist in the Mathematics and the Computer Science Division of the Argonne National Lab, and she is also a senior scientist in the Department of Computer Science at the University of Chicago. Chief software architect for Flash. Flash is a multiphysics, multi-scale HPC software that is used by several science and engineering domains. Anshu is interested in all aspects of HPC scientific software with an emphasis on design, productivity, and sustainability issues. We have issued more than 150 tickets for this webinar today, and all attendees have been muted. We will be receiving questions through the Zoom chat and also Google Doc. I have already pasted these addresses in the chat, but I'll do it again for people who joined us later. And the webinar will have breaks so Anshu can respond to the questions that can. With that, Anshu, I'll stop my sharing and please take over.
Thank you. Good morning, everyone, and welcome to this webinar. And just for a few moments until I find the appropriate screen to share. So hopefully you can see my screen now. And hopefully everyone can hear me fine.
Yes.
So before I start the webinar, thank you, Osni, for the introduction. Before I start the webinar, I will say that there are two distinct portions of this webinar, and I will stop after the first portion to take any questions that have come up until then. And I don't know why my slides are advancing by themselves. Hopefully they let me control for the most part. Anyways, to get on with the seminar. So the reason why one has to be worried about design in scientific computing is because of this positive feedback loop that you can see. It is that we start with a code and we run certain simulations, and it turns out that with these simulations, the scientific understanding grows. Once the scientific understanding has grown, so when we start out with the model, we usually make many approximations because we're exploring. As the understanding grows, we start removing these approximations, and therefore the model becomes a higher fidelity model. A higher fidelity model means that in the code, normally we're bringing in more diverse solvers. As we make the code more complex and we want to do bigger and bigger simulations, we need to make use of more hardware resources. When we do that, that leads to more scientific understanding. And so this whole positive feedback loop cycle just keeps going. So this is where HPC computational science has been the first part here until recently. That is the distributed memory model, where mostly the abstract programming model to which we were programming was pretty simple in that you assumed that the MPI was an adequate programming model, and that's all one had to worry about. And if you got your code working well with respect to MPI, you could by and large keep increasing the software complexity without having to worry about the large parallel programming model within your code. That changed with the advent of heterogeneous model, and now we are in this regime where it is not just the software complexity that is increasing continuously, it is also the platform complexity that is increasing, and we are dealing with two orthogonal axes of complexity, both of which we have to deal with. Added to that is this issue that all of the software that is used for exploratory purposes faces is that many of these components by themselves may be under research, and therefore the software continuously evolves. The other thing is that I at least don't know of any instances where the software was used in exactly the same way for two different science campaigns. Every use cases are different and unique. So every time there is some customization needed, and that also keeps growing both the complexity and the size of the software. So this is all been sort of crystallized or gelled in the context of US exascale computing project, which is at the forefront of many of these challenges because the objective of the ECP is to have participating applications and software technologies needed for their science be ready for the exascale platforms. And so there are about 26 applications projects and a whole host of software technology projects that are involved that are working towards making these software ready to work on the exascale platforms. So, and if you want to get more information about ECP, that is the website. And again, in the last slide, this website will be up as I take more questions. So this summer, as a part of the ECP project and basically sponsored by the IDEAS project, we had a series on performance portability. This was basically a series that had an introductory webinar by the science directors of the DOE leadership computing facilities, followed by 4 panels in which different people from various applications projects and software technology projects participated. The motivation for the series was that platforms in the current environment of heterogeneous platforms, the platforms differ not only from one generation to the next, but also within the same generation. And therefore, what works well on one platform may not work equally well on others. When the ECP project started, there weren't too many approaches that were well understood in terms of what would work well. And therefore, the community has been experimenting with various approaches and therefore has acquired wisdom and experience with respect to these various approaches that are feasible. And so we felt that this wisdom should be shared as widely as possible, not just with the ECP project, but also outside projects that may benefit from learning the experiences of the ECP community. What we felt was that there was a need for in-depth discussions, and what we had originally envisioned for this interaction was a hackathon that wouldn't quite be a hackathon in the sense that you wouldn't actually sit down and work on code and develop codes, but that you would sit down and share ideas, lessons learned, find out what the gaps are, and discover opportunities for partnerships. Also, by this time, we had, but what ended up happening was that we got into this time of social distancing just as we were planning these workshops. And so instead of workshops, it turned into the panel series, and that became the best available alternative. So the outcomes of the panel series has been as we expected. We talked about lessons learned and gaps and opportunities for partnerships. Another thing that happened was that some basic principles for how to design software for performance portability also emerged. And so the link below is a presentation about the panel series that you can view. And again, this will be visible on the last slide. Again, as I'm doing question and answer session. So the general design principles for HPC software, as we have gelled from wide community experience as well as the general experience of the ECP projects, is that there are considerations and then they have implications on design. So the considerations are that very often these science teams are multidisciplinary teams, and therefore they have to worry about many facets of knowledge. And for any one person to know all of the facets of knowledge that need to be understood is not feasible. And therefore, the design implication is that there should be a separation of concerns built into the design that shields developers from knowing in detail about unnecessary complexities that they have to deal with. The second consideration is that there are 2 types of components in almost any code. whether it is explicitly stated or is implicit in the code, this is almost always true, is that there is a code that changes, that pertains to the infrastructure, which would include things like the discretization, the mesh, the IO, the runtime, etc. And then there are the code components that implement the science model, which are the actual equations that we are trying to solve. So that's where the numerical methods are. And so its design implication is that they should work with different life cycles, because the infrastructure is the long-lasting code that should get a more in-depth consideration of requirements and a consideration and looking at various options and a much more thorough exploration of the design space before it is hardened into an almost product that is not going to be changing very often through the life cycle of the entire software. And then there is the quick changing part, which is the science model. And that is quick changing because that is the part of the code that is typically under ongoing research and therefore needs frequent upgrading. And therefore this needs to have a much more nimble life cycle. The other part that usually distinguishes between these two types of components is that one of them is logically more complex, which is the infrastructure, and the other one is mathematically more complex. And so these reasons, they really do need to work with different life cycles. The third consideration is that irrespective of what is the intention of the original developers of the code, codes, if they survive beyond a few months and a couple of years, they grow. Because people find the code useful and therefore new ideas come. New ideas come, they lead to new features and people start to reuse the code. And therefore, one almost always has to plan for a code to grow, which means the design implication is that extensibility should be built into the DNA of the code, and which should be accounting for an ability to easily add new capabilities and to be able to customize existing capabilities as needed. So this particular picture sort of encompasses the general design principles for HPC scientific software, is that we treat research subject as models and numerics and client code that is mathematically complex. And there is the lower part, the one in the more stable, that is the infrastructure, data structure, and movement, etc. And they should be treated differently and encapsulated in such a way that a plug and play mode is enabled for the research code, the client code, which is the mathematically complex, and the one that is actually implementing the science that you're interested in doing. The things that apply to both types of code is, of course, that they should be in locally separable functional units of computation. They should be encoded in a framework. They should have well-defined interfaces, and they should all be differentiating between public and protected codes. These are the general software design principles that apply to all kinds of software, not just scientific software. But the other key thing to keep in mind always is that one shouldn't be designing to a specific programming model and fitting one's code design to it. One should really be understanding the requirements of the code, and one should be designing first, keeping those requirements in mind, and then apply programming model to the design instead of the other way around. So here is a design model for separation of concerns that has been found to be very useful by many science communities. Is that there is the infrastructure design where you do a requirements gathering, a much more thorough requirements gathering that translates into a software architecture and API design that is then implemented. And here is the feedback loop, because you test, you maintain, you augment, and you keep doing it. This is an ongoing process that is going on forever. The capabilities or the numerics can be developed initially almost separately from the infrastructure if we have got the design right. So this can be done with Python, MATLAB, anything that people are comfortable with. They can design their numerics, develop, validate it against the models that they're interested in, and then they have to consider how to translate that into a code that becomes a component of the overall code here. And so the places where it needs to interact with the overall code is in the API through which it is interacting with the infrastructure and the framework, and then integrating it into the existing software architecture and framework. Now, the augment word here comes in because there are times when a new capability addition may need some augmentation to the API design because of specific requirements that the new module is placing on the infrastructure. And that's why there is this feedback loop where you go back and look at the requirements and you enhance the software architecture API design as needed. So an example from a domain that I'm very familiar with, and this is the multiphysics partial differential equations. This is still in the context of distributed memory parallelism only. So here what we have is a code, and we are looking at taking two different distinct views of it. There is the spatial decomposition, which returns a virtual view as domain sections. This is the domain decomposition. So domain sections where each section becomes a standalone computation unit. And this is especially true if you're working with, for example, explicit methods. So the black cells here are the cells that are updated by the physics operator, and blue cells are the ones that are obtained from neighboring components of the domain or the physical boundary, and they act as ghost cells. We're all very familiar with this concept of ghost cells, right? But the important thing to note here is, as far as the physics operators are concerned, it has no way of distinguishing between this as a domain component versus the entire domain. And that's why this becomes a virtual view, because each operator thinks that it is operating on the entire domain. And then because we are dealing with multiphysics, because we are dealing with multiphysics applications, there is a functional decomposition which normally manifests itself in form of an operator split, and that becomes a virtual view that is a collection of components. And so this is how the separation of concern happens, is that the parallelization and scaling optimization can happen at the level of domain decomposition, whereas memory access and compute optimization can happen at the level of each individual operator and function. And the separation of concerns, if implemented successfully, then results in domain experts and applied mathematicians implementing the functions and the software and performance engineers working towards the optimization without necessarily needing to know in detail the part that the other group of people is doing. So here is a design for extensibility from Flash, which had the extensibility built into it. And you don't really need to see the details of any of these, that these are there just to demonstrate the concept. So Flash got designed for extensibility because the assumption was that capabilities will be added for better models in future. So this is what is an example. Suppose if we start out with a code that just has a driver and a grid. Now we want to add a hydrodynamic solver to it. So to this code, the changes that need to happen is this entire code, the hydrodynamic solver, can be developed separately. It decides which of its functionality it wants to publish as the API. It decides which of the API, grid API functionalities that it needs to use. And the only changes that need to happen to the base code is that the driver needs to know that a new capability has been added, and therefore it needs to invoke that. And all of the other change happens transparent to the actual source code, because that is done through this configuration DSL that Flash has called the setup script, which is where the meta information about what any of the code components need is encoded. This meta information, such as these are the code units that it needs to work appropriately. This is the default. This is the other components that it won't work with. These are the state variables it needs to incorporate, etc. So this is a decentralized maintenance of metadata, which effectively allows this kind of addition of an entirely new capability without having to significantly alter the existing code base. So this is the key idea, is to distribute the intelligence, and that leads to an extensible code. This kind of an investment was extremely useful. Actually, about in 2015-2016 timeframe, we did a systematic study based upon the data that was available of the user base and the people that had been at the center. So we analyzed that data to actually quantify the impact that the investment in design had done. So the table that you see here, in that table where you see a year, that is the year in which that particular capability was introduced into the code by the community that is listed in the rows. So in 1998, for the astrophysics community developed compressible hydrodynamics. The stars are the other science communities that use that particular capability and therefore have benefited from having that capability in the code. So the takeaway from this table is the density of the stars that exist that clearly show the synergies that are exploited, and the amount of effort that was saved by the other communities in terms of developing their own infrastructure and their own capabilities. So an analysis showed that even if the other communities reused only 75% of the infrastructure that was developed, and not even any of the capabilities, as in these stars, they already had a saving of roughly 40 person-years per new domain. And when you add all of the physics capabilities that are reusable, the impact becomes even stronger. And this graph on the right shows the penetration of the code in other communities. So as you can see, the first part shows the share in 2005, and the second, the purple here shows the share in 2015, which is when we collected this data. And as you can see, that the code has just been growing in several other communities as a result of investment for hydrodynamics, astrophysics. So the takeaways until now is, for the software design, we need to differentiate between slow changing and fast changing components of the code. We should understand the requirements of the infrastructure and implement the separation of concern as a first class concern in the design of the infrastructure. One should design with portability, extensibility, reproducibility, and maintainability in mind. And one should not design with a specific programming model. The design should come first, and its implementation into a programming model should be the second step. So that concludes the first portion of the webinar, and I can take any questions if there are any so far.
We are good, Anshu. You can continue, please.
Oh, there are no questions? Okay. So now we are in the new paradigm because of platform heterogeneity. Now the software complexity is increasing as before because of the positive feedback loop cycle that we saw before. But simultaneously, the software developers are faced with a completely new challenge, and that is that the platforms are heterogeneous, and therefore the software itself has to deal with heterogeneous programming models. So the question that we are faced with is, do the design principles change? And the answer is not really. What actually ends up happening is that the details get more involved. So if we go back to the figure that we had about separation of concerns and the design model for separation of concerns, the purple ellipses are shown where the changes are needed, and the most extensive changes are likely to happen in this integration part, because the software architecture and API design is, it needs to be a little bit more intrusive and a little bit more intelligent in the design. And what do I mean? So before I go into what I mean by exactly that, here is a design guidance that got articulated in the ECP Performance Portability panel series that I mentioned earlier in the presentation. These were the points gelled by the participants, is that one should think of when they're designing, the design should be for hierarchical parallelism, which means that we should be thinking about several thousand threads operating simultaneously. The platforms are going to have hierarchical memory spaces, so that should be a part of the consideration. And therefore, the design patterns that we use should be thinking about counting, allocating, and reusing memory smartly, because memory itself exists in a hierarchical space. But a very important one is that any non-portable vendor-specific options should not be exposed in the design. And this is critical because as soon as you start to have any non-portable options in your design, you tie yourself to a specific platform or a specific programming model that can prove to be detrimental later on in the life cycle of the code. So to go back to what I meant by what needs to change in the software architecture. So if we look back at our initial decomposition, the spatial decomposition and the functional decomposition, additional things that are needed in the virtual view of the component is that we need more abstractions at solver level now, which means that it should be possible to encode the computations in a way that code transformation tools are able to specialize for specific target architectures, as opposed to having to maintain multiple alternative versions of the same code for different target architectures. So ideally, what we want to do is have one implementation which can be specialized by code transformation tools for the target architecture. Similarly, as we get more and more resources that need to be managed in more asynchronous fashion, because now we are dealing with nodes that have a whole bunch of devices. And so you actually have to think about how is the computation going to be distributed among these various devices. So what kind of data movement needs to happen? What kind of offloading and scaling optimization needs to happen? And so the consideration for load distribution come in, and some form of a runtime management also needs to come in, which both of these, the runtime management and code transformation and load distribution, should ideally still be a part of the infrastructure in such a way that a casual user, and I emphasize casual user because a graded access is useful, that a casual user need not have to know all of the details in order to be able to make modifications to the science codes. So in context to that, there is, so the whole question works around the question of portability and performance portability. So historically, when we were in the roughly uniform abstract machine model to which we were coding, we actually hand-tuned the code for the target. And some teams are still doing it, and this is the right option for some teams because their code base is either the entire code base is small enough, or they have distinct hotspots in their code that are small enough that it is not too much of a tax on the team to have multiple alternative versions for different target platforms. The current trend for anything except those teams that can get away with still hand-tuning the code is to have either multiple implementations or use third-party abstraction tools which aim to hide all of the details of the platform from the user. However, more and more people are coming to this conclusion that neither of those in the current trend, having multiple alternatives or using third-party abstractions that completely hide all of the detail and leave all the domain knowledge on the table, might be the best solution. So there is an intermediate option. And this intermediate option is for people to know and understand their code and refactor the code whereby they expose opportunities for use of abstractions. And also, as they are exposing these opportunities for use of abstractions, that they should also figure out the parameters, the right kind of parameters using which these abstractions can be plugged into their design. It's, I think, almost a given that some sort of a composability should be built into infrastructure, because component-based code and composability is key to minimizing the code that has to be either specialized or duplicated in order to obtain good performance on these heterogeneous platforms. And the third part is that one need not rely on these really all or none abstraction models, but that if one understands the abstractions that one has to use, then one can make tools or leverage community tools that let you hand tune without all the pain of having to hand tune. So what you can make happen is that instead of having an all-in-one magic compiler or a magic code transformer or a magic abstraction tool solution, that you work towards refactoring your code so that the hand tuning for specific platforms, quite a bit of it is automated and lets you do it quickly and more productively. So the underlying ideas for what I'm talking about are that what we ideally want to do is make the same code work on different devices, which means that we want to be able to express code in a way that lets compiler know that this expression can be specialized in many ways. And then we can just have multiple instances of code for those specialization. This is what a lot of the C++ based abstraction layers are doing through template metaprogramming. A lot of also what the abstraction layers are doing through that are providing the functionality for is how to assign work within the node. And so they are building what they call parallel force, or they translate, so they provide parallel forces constructs, or they provide ways through which directives can be used with unified memory. Or if the unified memory is not being used, then the directives for or specific programming model that can do explicit data movement. In many cases, that is an adequate solution, but if one wants to have a more complex data orchestration, if the application demands more orchestration, complex data orchestration, then that orchestration system has to be built. And that is very much specific application dependent. And it is my very firm opinion that every application should just pick up a solution that's complex enough and no more complex than needed for their own purposes. So how do we go about designing? We go about designing by looking at what is needed. We design for commonalities and we encode them. And how do we do that? If we view what the abstraction layers would do in our running example of multiphysics PDEs, we think about how do the abstraction layers are usually working. What they're doing is they are trying to infer the structure of the code. They are trying to infer what would be a good map between algorithms and devices. They are trying to infer the data movements that happen between various components of the code and between devices. They are mapping computations to devices. And these things, the application programmer is communicating this information to the abstraction layer through either constructs that these abstraction layers provide or through pragmas. And ultimately, the performance that a code is able to obtain depends upon how well this mapping is done. So here is an example of steps that one would take. And I'm just focusing right now on having one code that can be specialized for specific target architectures. This is not going into the runtime orchestration because that is much more complex and beyond the scope of this webinar. I mean, I cannot possibly talk about that within 1 hour, but I can definitely walk you through an example of a simple abstraction, refactoring of code and abstraction that allows you to have a single implementation of your basic core functionality without having to have a heavyweight abstraction layer or tools involved. So this is a Fortran example with a simple key dictionary, and the details of the calculations are unimportant. The things that I would like you to focus on are the state variables, the arrays involved, and the temporaries involved. So this is a subroutine. It has these arguments which are coming in. So this is the first box has the code for CPU, the second box has the code for GPU. At the CPU code, the temporaries are coming in as single dimensional arrays. In the GPU code, the temporaries are coming in as 4-dimensional arrays. That one dimension that is coming in here in the CPU code is the dimension for state variables. So somewhere outside of this particular subroutine, these the state variables have been copied into these temporaries U plus, U minus, and flux, and they're handed to this subroutine. Now, it turns out that the optimal use for the CPU is for this to happen with a single dimensional, with this formulation of the arrays, whereas for the GPU, it is more optimal for the entire space of the data, including the spatial dimensions, to be operated on at the same time. So here we are looking at temporaries that need to have different data structures. We need to have arguments and interfaces that do not look anything like each other. And the only thing that is common is this actual calculation. This is identical between the two. And this is where actually the meat of the code is. Everything else is just control and logic. So what do? The first step is we define keys that take care of temporaries and arguments, where the key definitions are different for CPU and GPU. So the key definitions for CPU for arguments is just this list. So all that I have done, if you look at the previous slide, is I've taken this entire argument list from here and from here and defined that as keys that are different, that are different for the CPU and the GPU. And I did the same thing for the declarations that need to occur in between the CPU and the GPU. The second part of it is that I need to have different definitions for the constructs also. And so there are some constructs that are only needed for the GPU kernels, whereas some constructs are needed for both CPU and GPU. In this instance, I picked up the definitions that need explicit definitions only for the GPU. So we make provision for null implementations, which means when these keys are encountered by the translator, they're simply ignored. So with these, armed with now these definitions, what we can do is we can refactor and rewrite our code in this format, where the @ symbol is just indicating to the translator tool that just to replace the regular expression that it is encountering by the corresponding definition. And so now we have a single code, which is a subroutine definition, which can be specialized to work equally well on CPUs and GPUs through a simple transformation that occurs before the build, not even at the runtime, but at configuration time. And the tool is extremely simple. It is just a key dictionary from Python. So ideally, whether one is doing it with such simple tools one writes, or leveraging community tools, or using abstraction tools like Cocos and Raja, good result can only be obtained if one goes through a similar exercise of locating good use of abstractions and that's the only way of obtaining good results from third-party abstraction tools. So to go back to what we talked about, the approach to portability, one of the highlights that came from the panel series and was articulated by the developers of Cocos and Raja was that those users who went through a similar exercise of understanding the abstractions needed in their code and took steps of refactoring and designing their code appropriately, derived greater benefit if they understood their code structure and needs. Or in other words, the codes that really thought about their design derived greater benefits from, greater benefits even from Cocos and Raja. So that brings me to my final takeaways, and that is the key to both performance portability and longevity is careful software design. There is no substitute for understanding your code and doing the appropriate things with the, in terms of refactoring, etc., with the code for the software design. The extensibility should absolutely be built into design. Design should be independent of any specific programming model, and the composability and flexibility built into the design help with performance portability too, performance portability of the code. Notice that these takeaways are not so very different from the takeaways that I articulated after the first stage of this talk. And as I mentioned before, that what has changed between what those takeaways were and what these takeaways is that it is only the details that matter, but the basic design principles of separation of concerns, of minimizing complexity where possible, of not leaving out any domain knowledge on the table are all equally useful. So then there are these resources. The details about exascale computing project are available through this. This link points to a presentation given at P3HPC workshop on the outcomes, inferences, and format of the exascale computing panel series. So if you want to find out more about it, this is the right place to go. I have also been giving, as a part of Better Scientific Software tutorial, I've also been giving a tutorial on software design for exploratory and scientific software. And this link points to that presentation. And also later, as they become available, there will be videos of similar tutorial presented at Argonne Training Program for Extreme Scale Computing Science in 2020 that also covers concepts of design. Recently, in preparation for this presentation, I also wrote a blog article based upon the performance portability as discussed and as it came out of the performance portability series. And this is a link to Cocos if people want to find out, because Cocos is the most well-known abstraction layer that people are using and deriving a great deal of benefit from using. So this points to Cocos. And that brings me to the end of my presentation. I'm happy to take questions.
Thank you, Anshu. Yes, we have some questions here for you. So the first one is, you suggest, in quotes, to design with reproducibility in mind, close quotes. So what are the greatest challenges to design with reproducibility in mind, given the different available platforms, compilers, and the programming models?
So designing for, there is a difference between reproducibility, replicability, and there is one more word that I'm missing. So some people consider reproducibility to be a bitwise reproducible exact result. And I am not talking about that, because in real science world, other than to verify and validate your code, the bitwise reproducibility really doesn't mean anything because all of our models are approximate. And so in scientific terms, what is important is to be able to reproduce scientific inferences that are qualitatively similar to the inferences that were brought about by, so if different people do a similar study, that the qualitative inferences that they draw by following the same steps are the same. And so that is what I'm talking about when I talk about reproducibility. And that should not be in any way diminished by heterogeneity in platforms.
Okay, so one participant asked for examples of the abstraction, but I think you had the slides covering those. So the next question then, why use a new language for those keys, right, instead of a standard preprocessor?
I am not sure I understand the question. What new language?
The participant is typing. You know, the at symbol, the at syntax.
Oh, that's just, that is not a new language. That is just simply a pre-processing step that will replace the key with the corresponding definition of that key. And to give a very blunt answer to the question is that any of the languages that allow for this kind of programming, this kind of template metaprogramming, is only available in C++. And so that really is not an option available to the code bases that are already very huge in any language other than C++. So what I'm trying to demonstrate is that it isn't necessary that you translate your entire code to C++ in order to be able to implement these kinds of abstractions.
Right, and to continue that question here, what the participant was typing, so, but the comment is that this is not a FPP or GNU CPP, so it's a kind of in-house solution, is that correct?
So this is true because CPP or whatever the preprocessors that exist may not exactly match the what you need to do in your code. Because, for example, the solution that I showed, and let me go back to the slide, is that this is using inlining. And in addition to that, where I have used it, this is using not just inlining, it is also allowing for arguments, and it is allowing for recursion. And these three features together are able to give me all of the functionality that I need in order to do this kind of abstraction. And let me say that this is I recently learned about another team that is taking a very similar approach, and this team is from Norway. And what they're doing is they effectively have a DSL for their own purposes that is entirely built on such preprocessor and macros. But basically what this does is it frees you from having to translate your code to a completely new, to a language. So the context in which we developed this Flash, that's a 1.5 million line code written in Fortran. And given a choice between developing this tool, which took less than 2 weeks to develop, test, and 1 week to change the code in order to deploy it, that's a much more attractive option. But in any case, that's just a detail. The point is whether you use existing template metaprogramming and the abstraction tools, or you do roll your own solution like this, the thing that you cannot avoid doing and you should not avoid doing is thinking through the structure of your code and what is the appropriate level at which abstractions should plug in, and where should you plug in those abstractions.
Right, another question here, Anshu. So what do you think of the potential of a very high level languages like Julia, where the compiler can figure out optimal implementations by analyzing the full dependencies of the code?
That is utopia. And I'm not holding my breath for that kind of utopia, because in my experience, the biggest reason why these domain specific or simpler tools can be more efficient is because we already know our corner cases, and therefore whatever tools are getting developed don't have to account for those specific corner cases. Whereas any general purpose tool has to make conservative assumptions and has to account for all of these corner cases, and therefore consequently becomes more and more complex. Now, as far as the compilers are concerned, even till today, the compilers, even for the simplest cache hierarchy cases, were not able to successfully optimize codes automatically in way that hand optimizations brought about, which is why people kept doing hand optimization. And that was a much simpler exercise for the compilers to do. And therefore, I think even within the compiler community, more and more people are coming to this conclusion that a magic compiler is a holy grail, which is not very easy to achieve and is not likely to happen anytime soon. And that one has to, and because there are many orthogonal concerns in code optimization, that really there should be an orthogonal performance optimization approach in the tool set as well. And so the newer efforts that one hears about, for example, one that is in ETH called DAYS, and then there is another new one starting at Koç University in Turkey, and this is what my collaborator from Tokyo Tech is interested in working on, is to have a chain of tools, each one focusing on one concern of the performance, and not let any one of those one tools be extremely complex, but that combined together, when they are applied, they provide flexibility and power of optimization without making any single tool too intelligent or too complex.
Okay, I don't think we have an additional question here. I don't see anything coming in the chat or in the Google Doc. With that, Anshu, could you please stop your sharing? So I'd like to announce the next webinar.
Yes.
Okay. So thank you very much, Anshu, for this nice webinar. I'd like to thank all the participants also for joining us today. Again, so I'd like to improve the series. You can give us feedback through this short survey. The slides I'm recording are going to be available at these two websites. Actually, the slides are already available there at exascaleproject.org, Advanced Software Design. So the next webinar in the series is going to already be 2021, January 13th, Extreme Scale Scientific Software Stack, E4S. And then that webinar is going to be presented by Samir Shandy and David Rogers. So you can keep track of all the future events by visiting exascaleproject.org. And I'd like to wish all of you a very nice holiday season and Happy New Year, and see you in January. Thank you all. Thank you, Anshu.